Alright class, today we are going to talk about dynamics and Newton's laws. So this is going to be titled Newton's laws. Newton's laws have to do with dynamics. Dynamics basically is why things move the way they do. And it all has to do with forces. And a force is a push or a pull. And we have several different types, and those should be separated. I don't separate my A's very well from my words. A push or a pull. We have several types of forces we're going to be talking about. So I'm going to list them here for you. Types of forces. The first one is tension. And whenever we have tension, you'll label that on a picture or a diagram. A big F with a capital T is a subscript. And an example of that will be a rope or wire to pull or hold an object. Our second force is the force of gravity. You will label that capital F, little g, as a subscript. And that is the earth exerting a downward pull. The third force is air resistance. We will label that F with a subscript capital A, and that is when air exerts an upward force The fourth force is the normal force. We label that capital F, capital N as a subscript, and basically that's a supporting force. So that would be something the floor exerts on the object to support it, or a table supporting an object. The fifth force is frictional force. And that will be labeled with a capital F, a subscript little f, and that is force opposing any applied force and we need to talk about frictional force because it can be split up into two different forces. You have your static friction. Sometimes we know what it is, and sometimes we just want to label it as an F, little f. Static friction will be labeled as a capital F with a subscript S, and it is friction to keep an object in place. So you have static friction between the table and this paper right here. It's keeping my paper in place. And then we have kinetic friction. And it is sliding friction. So anytime you're sliding an object, you're going to have kinetic friction. So it's friction of movement. Now let's talk about Newton's laws. Again, you can pause these to finish these notes up, but I'm going to move along. We have 3 Newton's laws. We have the first law, an object will continue in its state of motion unless compelled to change by a force impressed upon it. We often call this the law of inertia. Which is resistance to change of motion. There's the second law. The sum of the forces equal mass times acceleration. And we need to talk about mass here. Mass is not the same thing as weight. Mass is a quantitative measure of its inertia. So basically, it depends on how much mass it has as to the resistance to the change of motion. So mass is important to inertia. I want to cover here what the units are for your force. Your force is units. Your force is mass times acceleration. Your units for mass here will be kilograms. And then for acceleration, it's meters over second square. So kilograms, meters over second square. A kilogram meter over second square equals 1 Newton. So anytime you see kilogram meter over second square, you want to change that to a Newton. Then you have the third law. To every action, there is an equal but opposite reaction. We will be using this one a lot. All right, let's talk about, since we talked about mass, let's talk about weight. Weight is different than mass. Weight is the mass of an object with the gravitational force applied. So basically, it's your mass and gravity acting on your mass. That's your weight. So when you weigh yourself, you're taking gravity into effect. And we will show your force of weight is mass times gravity. Or it can be written as the force of gravity equals mass times gravity. Let me just summarize the formulas here that you're going to be using in these problems. We're going to have F of X equals MA, and that stands for the sum of. the sum of the forces. The sum of the forces in the y direction equals ma. We're going to have the force of gravity, which equals mg, or the force of weight equals mg. And then we've got forces for static and kinetic friction. Mu s times the normal force, and that is a u with two tails. We call it mu. Or the force of kinetic friction is mu k F of n. What this mu stands for, it's called the coefficient of friction. And it's one of those things that's like a fingerprint. Everything like wood has the same coefficient of friction always, like and it depends on the type of wood. Like elm wood has a certain coefficient of friction and it never changes, and oak has the same coefficient of friction, it never changes. Certain kind of plastics have the same coefficient of friction, it never changes. Certain metals like steel have a certain coefficient of friction that never changes. And so this is actually like a fingerprint of the substance that is, or the object that is in the problem that we are working. And a lot of times that will be given to you, or you will be given a table in which it is in and you can look it up, or they have tables that you can look up on the internet or Google to find out their coefficients of static and kinetic friction. Okay, let's go on to work some problems, some example problems. My first example problem, a can of paint with mass of 6 kilograms hangs from a rope. If the can is to be pulled up to a rooftop with an acceleration of 1 meter per second squared, what must the tension in the rope be? Okay, the first thing I want to do whenever I'm working problems like this is to draw a picture. So I'm going to just draw what we call a free body diagram. And it's just a dot which shows the object, and this object has mass, and it's hanging from a rope. So we will draw a line for the rope, and there's an arrow pointing up because the rope is connected up here somewhere. And we call that, we label that the force of tension. And then we have a force pulling down on this can of paint, and it's the force of weight or of gravity. So we label it F with the subscript W. So the first thing you always want to do when you're working problems in this unit, and pretty much from now on, is to draw a picture. And you want to represent the object of interest as a heavy dot, and draw the forces that act on the object as arrows connected to the dot. This is called a free body diagram. We're going to call the up positive and the down negative. And so whenever we write the sum of the forces, we only have forces in the y direction. So we're going to write the sum of the forces in the y direction. We know that equals mass times acceleration. And our sum of the forces in the y direction are basically Ft minus Fw, and that equals ma. Then we're wanting to solve for the tension here. So we want to manipulate this for the tension. So we want to move Fw over to the other side. So that's going to become a positive Fw plus ma. And now we can substitute our formula that I gave you on the previous page for Fw. So Ft equals mg plus ma. Which we can then pull the m out, and we have g plus a, g plus a. Make that a little plus. I can rewrite it, g plus a. I got ahead of myself. And then I can start adding in my numbers here. My mass is 6 kilograms. My gravity is going to be a 10. We're going to use 10. And then the acceleration is 1. And we're just looking for the force of the tension, and it's positive. So we want to use a positive gravity here. And we just want to use the magnitude of the gravity, really. And so 10 plus 1 is equal to 11 times 6 is going to be 66. And it's going to be newtons. And I can show that because gravity is m over s squared. 1 is m over s squared. And so you have a kilogram meter over second square, which is a newton. So there's the first example. Let's look at one more. Crate of mass 20 kilograms is sliding across a wooden floor. The coefficient of kinetic friction between the crate and the floor is 0.3. So see, we got the coefficient of friction. Determine the strength of the friction force acting on the crate. Okay, so the first thing we want to do is draw a free body diagram. My dot is going to represent my crate. I can also draw a crate if I'd like, and a floor. And it is sliding across a wooden floor. So I've got some type of applied force. So I'm just going to use F here. And I know I have some friction. So if it's sliding in that direction, then the friction is going to be opposing that. And it's kinetic friction, so I'm going to use F of K here. Then I've got the force of its weight. And I've got the supporting force of the floor. So the normal force, F sub n. So I actually have a lot of forces acting on this crate. We'll see if we need them all. The normal force on the object balances the object's weight. So we can look at the sum of the forces in the y direction equals ma. However, the crate is not moving up or down. So your acceleration in the y direction is actually going to be 0. But we know that we have the forces in the y direction, we have mg. So we can say that mg, if we substitute the mg for the force here, then is equal to 20 kilograms times 10 meters per second squared. And so we have 200 newtons here. We have to get the normal force here for us to use for the kinetic friction. So we have basically F of n minus F of w equals 0. We move F of w over to the other side, and that's how we get what we got here. So F of n equals here F of w, which is mg. So I should have probably showed that step. Alright, so then we have the sum of the forces in the x direction. That's equal to ma. What are the sum of the forces in the x direction? Well, we'll call this side positive and this side negative. So we have F minus F of K equals ma, and we know we do have movement, so there is going to be some type of an acceleration. And we are looking for the strength of the frictional force. So I'm sorry if you're hearing a bunch of noise. The bell just let out. So we have coefficient of kinetic friction between the force and the crate, and we are looking for the strength of the frictional force acting on the crate. So we're going to have here I'm sorry, we don't even need this step right here. So let's mark that out. Here I'm jumping ahead. Once we figure out the normal force, we can figure out the frictional force by using the formula that I gave you earlier. The force of kinetic friction is equal to mu k over F, or times F of n. And we got F of n here, and we have mu, which is 0.3. 0.3 times our F of n, and that gives us the kinetic friction. So that is going to equal 60 newtons. So I was trying to jump ahead and figure out the kinetic friction from some of the forces in the x direction, and I did not even need to do that, because as long as I have the normal force and the coefficient of friction, which I had forgot they gave us, then that's all I need to figure out our forces on our kinetic frictional force. So those are a couple of problems there for you to take a look at, and I will see you back in class, and we will practice these starting next week. Bye-bye.